Good morning, everybody. I'm Ushasri, working as Assistant Professor in the Department of Biomedical Engineering. Today, I'm going to tell about the classification of biomaterials, which is a topic in the coursework of Biomaterials. It is a course offered to the biomedical engineering students, and today we will be discussing about the importance of biomaterial in the medical field and as well as the various types of materials which are used, what are their advantages, disadvantages. Biomaterials is a material which is to be work in friendly with the host tissue. That is, when an implant is to be implanted inside the body, we have to assure that the material which is used to make the device and which is implanted inside the body should not show any adverse effect into the host environment. That is the tissue which is coming in contact with it. So, when this material is to be selected as an implant material, prior to that, we need to assess its properties, how far it will be compatible with the tissue, and if whether it is compatible or not, if in case it is compatible, to what extent. So this knowledge is very important for the biomedical engineer to devise or to select a particular material to devise an implant. And this implant material would be selected on several other considerations also, which we will be looking further. So, knowing what a material is, how it functions inside the body, we will be able to understand, or the student after the main objective of the course is to make the student understand about various types of materials, and when it is coming in contact with the host tissue, what is the tissue material interface and the interactions at that interface, and based upon that we will be evaluating whether it is compatible or not, and we call this term as biocompatibility. Once it is understood that it is biocompatible and can be used for the medical purposes, or that is to implant inside the human tissue, then we will be going for the different applications wherein we will be using the material for both therapeutic as well as diagnostic purposes. So after completing the course, the outcome of the course would be the student would be able to identify the suitable material based upon its characteristics, whether it is suitable for the given application or not, and also will be able to evaluate the biocompatibility and assess it in terms of both in vitro and in vivo, wherein in vitro is outside application and in vitro is an implantable device which is to be implanted inside the body. So here, as the human body composes of different types of tissue, so selection of a material with respect to the type of tissue which is coming in contact with the implant material would be very crucial. So the hard tissue and soft tissue, if we broadly classify, the tissue present in the human body would be both soft tissue as well as hard tissue. And if, for example, in the hard tissue, it would be bone and the tooth, and all other soft tissues like organs, muscle, skin, all those would be coming under soft tissue. So if a material is to be designed and selected for soft tissue, what should be its characteristics, and if it is a material to be selected for a hard tissue replacement, how should be its characteristics, that will be able to assessed by the engineer, and thereby proper selection of the material can be made. So in the present topic, we will be able to understand what is the basic definition of a biomaterial and what are the different classes of materials that are biocompatible in nature, as well as synthetic, which can be used for various therapeutic and diagnostic applications in the medical field. Biomaterial is a synthetic material which is used to replace part of the living system which is damaged or diseased, and in order to replace its function when it is coming in close contact with the living tissue. Meaning that a material or if a tissue is damaged to some extent and we want to remove that tissue and assist that with a additional artificial synthetic material, then that would be called as a biomaterial. In the process, it also has to satisfy biocompatibility feature, wherein the material after coming in contact with the tissue should not show any adverse effects. It may be, this material may be a direct natural material like cotton, silk, which can be directly taken from the nature, which is biocompatible in characteristics, and thereby it can be directly used. Example, sutures. Whereas few of the materials cannot be directly used from the nature, though they are available, but they cannot be taken into the body directly. So they need to modify. So in a term wherein we have to overcome the disadvantages and enhance the feature of biocompatibility in those materials. So all these topics would be covered in the coming session. And coming to the definition, it is a synthetic material which is used to replace the diseased or damaged tissue and also function in place of that to deliver the functionality of the tissue. It may be a natural material, synthetic material, or a modified version, or an extracted one, or an engineered one. Any sort of material which is having high biocompatible will be of prime choice. And once placed into the body, in the host environment, that is the host tissue environment, it has to function in place of that damaged tissue. If it is a partly, then the function would be partial, and if the entire tissue is damaged, it need to be replaced completely and it has to take up the function on the whole. Thereby, we can classify the materials based upon their performance and based upon their biocompatibility level. We can make use of them both for therapeutic and diagnostic purposes. So as we have discussed what a biomaterial is and what are its considerations, and for it to be used inside the body, what should be the requirements, that will be discussed now. As previously discussed, biocompatibility. Biocompatibility is defined as the interaction between the biological tissue and the biomaterial. Biological tissue is the host tissue. When the implant is placed inside the body, the implant will be coming in contact with the tissue. So that tissue which is coming in contact with the implant material is called as the host tissue. And the implant material would be any material, biomaterial, which is of prime usage in order to replace the diseased and damaged tissue. So how compatible they both are, that would be analyzed by studying the tissue material interface. What is that interface? How is it going to facilitate the function to be delivered? Whether it is feasible or is it resulting in any adverse interactions causing toxic, allergic, carcinogenic, pyrogenic, any such reactions in it or not. And all those things need to be assessed. So for it, a material to be selected as a biomaterial for a given application, it should be highly biocompatible. It should be pharmacologically acceptable such that it will not create any toxic, allergic or immunogenic or carcinogenic, etc. such reactions. And it should be on, this is towards the tissue part. Now when we take it to the tissue material interface, both the response of the tissue and the response of the implant material, both need to be considered. So tissue reactions are to be studied with respect to the above mentioned non-toxic, non-allergic, all such reactions. When coming to the material, even the material also should be very stable enough. In a sense, like it should be inert, should not get reacted, neither it should alter the tissue functionality, nor it should alter its own properties. That is also important. Only then we can say that the material is compatible for that application and it is biocompatible. So it should be chemically inert and stable in the host environment. And with respect to time also, it is not that soon after the implantation it is working fine. When an implant is implanted inside the body, that will be there for the entire life of the patient. So for that reason, in order to ensure that it functions well with respect to the host environment for the entire life of the patient, it should not get degraded with time. So the function of it should be very reliable and it should perfectly function on the day 1 to the last day of that patient. Apart from this is all these points are pertaining to the biocompatibility. Apart from biocompatibility, once it is being implanted inside the body, for example, orthopedic implant. So usually in the skeleton system, if any bone tissue is getting damaged, it will be affecting the posture, the movement of the patient. So when we want to replace that with an artificial material, so we should see that the material also gives adequate mechanical strength such that it allows us to move and do our day-to-day activities. And it should also have sufficient life, and this strength should be retained for the entire life of the patient. And coming to the weight and density, it should not be too heavy such that it will impose load on the tissue, and the tissue in turn gets damaged because of it. And coming to the commercial point of view, so for a material to get commercialized and used for various applications in the market, it need to be inexpensive. It should be able to reproducibility, and it should be able to fabricate very easily, and it should also be allow us to fabricate it in large mass productions. Such materials would be highly commercially successful when compared to the one which are very few and which have very few applications for them. Coming to the biocompatibility, as I told you, it is the interaction between the living tissue and the material, which forms the material tissue interface. So when a material is implanted inside the body and comes in contact with the host tissue, a tissue material interface is formed. Because of this tissue material interface, there will be few reactions which occur at the interface, and those reactions need to be assessed in order to evaluate whether the material is biocompatible or not. So for a material to be biocompatible, it should be ensuring that the tissue material interface is very stable, meaning that both the tissue as well as the material are not going to cause any adverse effect in the host environment. That is at the interface level. And it is chemically inert, stable, delivering the function properly for whatever function we want it to work, and therefore the host tissue is also safe enough, and it is not being damaged further, or ensuring that the material or the implant is functioning properly. On the other hand, if the tissue material interface is not stable, it would be resulting in various reactions, and those reactions would be evaluated both in terms of tissue response as well as implant response. In the tissue response, the tissue may get changed its characteristics, such as it may get into some allergic reaction, it may result in allergic reactions, it may become toxic, or it may get further damaged or killed, and it may result in some adverse mutational changes within the cell environment and its metabolism, all such which may further lead to carcinogenicity also, that is the cancer causal, and all such reactions would be pertaining towards the tissue response when the material and tissue interface is unstable. Coming to the implant material response, the implant may get corroded away, it may create some adverse chemical reactions wherein it will change the interface between the material as well as the tissue, and finally result into some inflammation, infection, and all those things. So like this, tissue material interface or the material tissue interface need to be studied in order to evaluate the biocompatibility. For us to select a material for a given application, we should ensure that the material is highly biocompatible with respect to that application, both in terms of tissue response as well as material response. So therefore, in order to analyze the level of biocompatibility a material offers for it to be selected for a given application, we need to study it in three different aspects. One is the host response, that is the tissue response with respect to biological tissue, which is coming in contact at the interface. And the other one is implant response with respect to implant characteristics, properties, and all those things. And finally, biocompatibility will be evaluated by studying the interaction between this biological tissue as well as the biomaterial. So having discussed so much about what a biomaterial is, how it is compatible or to what extent it is compatible, what are the requirements for it to be used as a biomaterial, we now get into the classification of biomaterials. What are the different types of materials available? What are their characteristics or the properties, advantages, disadvantages, applications, all those things. So before going into exactly classification, initially when the concept of using an artificial material or a synthetic material to replace the live tissue inside the body, naturally existing materials were taken into consideration. So if we take example, like sutures are best example. Sutures were the initial invention wherein an outside material, like which is not of living origin, would be used to work with the tissue and thereby help in healing. If a wound is kept open, it will heal. Nevertheless, because of the physiology pertaining to the healing mechanism, it will heal, but it will take more time. If you have a proper sealing agent wherein you seal the wound, it will be increasing the safety for the patient by avoiding infection of the wound site, and also help the wound to heal much faster. So that is how the use of additional material helps in delivering in the application and with enhanced safety for the patient. So to understand what are the different materials which can be used, first we start with the materials that are taken from the nature. And first category in the naturally available materials that can be used as biomaterials are polymers. So we know there are wide variety of polymers available in the nature in different forms and in different quantities, abundantly available. So it's a different issue where we can directly make use them for the application or not, or we should have fabricated and modified version of it can be used. So that again will be depending upon how biocompatible it is. If it is not compatible, how can we make that compatible enough? So that would be including the type of fabrication technology and the type of characterization technique which we use to make the material biocompatible. So to basically classify, polymers are the first category which are available in the nature and which are abundantly used for biomaterial applications in various applications. Main advantage of this is that they are resilient. They are very soft. They can easily be controlled, manageable, and ease of fabrication also is one other advantage which makes the polymers highly applicable as a biomaterial. So having these advantages, they are mainly used for sutures, blood vessels, and other soft tissue applications. So wherever we want, because as I discussed earlier, human body composes of different types of tissue. Bone tissue is a different tissue. It is a hard tissue. Even if we come to the soft tissue also, we have different types of tissue. Organ is a separate tissue. Muscle is a separate type of tissue. Blood vessel tissue is a separate tissue. Fat is a separate tissue. So like this, though all of them are categorized under soft tissues, each of the soft tissue has its own characteristics. So in order to satisfy the characteristic of these wide variety of soft tissues, obviously we need wide variety of polymers or the wide variety of materials. So for this, like, we will be using polymers. Example, nylon is a famous, or it is a very popular suturing material, even the polystyrene. And the silicone rubber is also used for implants, both for grafts and all those things. And polytetrafluoroethylene, it being a polymer, even then it will be used for hard tissue applications also, such as in implants, wherein we require few of the soft cushioning effects in the joints and all those things. So having discussed about the advantages, coming to the disadvantages, when I say they are resilient, they are very soft enough and they are at the same time weak. Weak in terms of they are highly sensitive to temperature, pH and other atmospheric condition. So any change in the environment condition or any change in these parameters, it will be changing its form and it will be getting degraded. So the life of a polymer is very limited. Few, they may sustain up to hours, few days and few to months and very hardly in years. So the major drawback which makes polymer as a limited source of biomaterial for application is its life. So since it is weak and it is easily degradable, it cannot be used for life sustaining applications, wherein we want the material to function for the entire life of the patient. So that becomes the major drawback for the polymers. And this degradation, if we are able to control, if we are able to modify, and if we are able to deliver or degrade it in a form wherein we want it to be retained for the desired time, if we are making that possible, or if we are modifying a material wherein we can control its degradation rate, yes, fine, we have such applications also. So for short-term applications, because example is suture itself. Suture itself is a short-term application. We may require the suturing material to hold the tissue in contact from for few days to months, depending upon the site and depending upon the severity of the incision made. So for that reason, yes, if we are able to control its degradation rate and make that sustain and with reliable performance for the desired time of days to a month or so, yes, they can be used. So that is another way how we overcome this disadvantage and make these polymers as a best suitable material for soft tissue replacements for a shorter duration of applications. Having discussed about polymers, next is the metals. Metals, we know, they occur naturally in the nature. So we get them in crude form. We can't make those crude materials to be used as a biomaterial, obviously. So we need some fabrication techniques to purify them, to modify them, to enhance their properties as desired by the application. So fabricating a metal when compared to polymer is highly difficult. Polymers are very resilient, they can easily fabricate into different forms, different shapes. But that is not the case with the metals. Metals are very strong enough, they are ductile, malleability, their ductility, malleability features are with respect to their melting points, because metals, obviously they being the solids and highly crystalline compound, they have high mechanical strength, and that's the reason the major advantage of metals are they being highly mechanically strong. So this mechanical strength, high mechanical strength of metals makes them to be used as orthopedic implant material, wherein the material, the implant material should withstand the loads, withstand the forces when we move, and also maintain the posture with respect to the load bearing effect. So all these applications or all these functions can be delivered by using metals. So that is the reason, because of their high mechanical strength, we will be using them for joint replacements and also for some other dental applications also, wherein we have dental root implants. So when we classify like applications into two categories, that is the hard tissue applications and soft tissue applications, joint replacements, that is the orthopedic applications, and the dental application, these two come under hard tissue replacements, and rest of the things will be coming under soft tissue replacements. So having discussed their advantages, their strength and their ability to convert them into fine wires and all those things, So if they can be fabricated into very fine wire sort of thing, they can even be used as suturing material. Example, pacemaker sutures, wherein we have to suture the pacemaker onto the heart muscle wall. So here if we use polymers, they degrade it fast, their lifetime is very small, and hence we cannot use polymers. Without suturing, the pacemaker will not retain there, and in order to securely fix the pacemaker onto the heart muscle tissue in order to pace it, yes, we need to suture it. So what is the material left? Metal. It being a strong one, yes, it retains there, it withstands the pressure, because heart is a continuously pumping organ. It will be continuously imposing forces and stress on the on these suture wires. So because of that high stress also, polymers cannot withstand such high stresses, and hence we'll be making use of these metals, those metals which can be finely drawn into fine wires, can be used as suture materials, especially for pacer, this pacemaker suturing wires. Another application is bone plates and screws. So when we defined biomaterial, we have also discussed like we want the synthetic material to replace the damaged tissue on the whole, partially, and also to support it. So if a part of the tissue is damaged, so it may be used to replace that partial application or partially damaged tissue and deliver its function on a required level. For example, of this bone plates and screws, if the bone is getting fractured, the bone gets healed up. Nevertheless, even if we don't support it also, it will get healed up. But the problem is, it will take much time, and it will not, it will be giving lot of pain to the patient, which is highly unbearable pain and discomfort to the patient, which the patient doesn't want to bear. And hence, in order to ease out his discomfort, we will be assisting this fracture, meaning that we are allowing the bone to heal naturally. But for that to happen faster and with less pain to the patient, we have to support that healing mechanism by applying few fixative devices. So meaning that when the bone is fractured and misaligned, we have to get into alignment and then apply some plates and then screw it up. So when we apply plate and screw it up, it will be making it inline, and thereby when it gets healed up, it will be giving a perfect shape for the bone, and there will not be any postural defects in the patient after healing. So coming to the disadvantages of metals, we have corrosion is the major disadvantage where we cannot use metals, because they being metals, they immediately react with the fluidic environment, and because of these oxidation reactions, the material tend to get corroded, and once corroded, that becomes highly dangerous for the tissue environment, wherein it will be releasing carcinogenic agents. So that's the reason, because of this corrosion effect, metals are limited for few of the applications. If we are able to overcome this, then we will be safely using metals for different applications. Coming to the ceramics and composites, these are engineered materials, wherein we make use of the advantages of polymers and metals and fabricate it or modify them in a way wherein we can overcome the disadvantages. So overcoming these disadvantages and making them perfectly used with respect to the merits they have, those will be designed as ceramics. So ceramics, since we are engineering it or making or fabricating it in an intention wherein we want to increase its biocompatibility, yes, these materials are highly biocompatible. And major application again, because we can overcome the corrosion part, they can safely be used for dental and orthopedic applications, which are again life-sustaining devices. They remain in the body for entire life of the patient. So there are also few disadvantages with ceramics. So because of these modification and it's using different fabrication technologies, in a process they become brittle and they are not that resilient to fabricate. And when compared to the compressive forces, tensile forces are very weakly handled, and in case of torsional forces, yes, they tend to break and they become brittle. So these are the disadvantages with the ceramics. Now coming with the composites, composites are also engineered materials, but their ability to be strong would be completely depending upon the fabrication technology. So how you are going to fabricate, it's an altogether a different composition, wherein we use two different materials and merge them in a way, like we have a reinforcement material and we have a matrix material. So the construction of a composite material itself is very special, and highly sophisticated fabrication technology will be involved in it, and hence their cost is also very high, and they are very difficult to make, since only very specific technology should be used for that. So examples for this is bone cement and dental resins. So having discussed about the four basic classes of biomaterials, now we quickly look into the examples of each category. In the metal, we have stainless steel, cobalt chromium alloys, and titanium alloys. These are very popular and were commercially available in the market, and they are widely used for dental applications as well as for the orthopedic applications. So coming to the stainless steel alloys, three types of stainless steels are used for this. And vanadium steel being the first one, it was, yes, mechanically strong and was highly useful in the orthopedic implants, but yet it was suffering from inadequate corrosion resistance, so it used to get easily corroded. So that's the reason a modified version of it, by alloying it with molybdenum, has enhanced corrosion resistance, and that was used. So 316S and 316L are those stainless steels. 316L, it is the carbon content was also included in it to give further resistance towards the corrosion. So basically, joint replacements, wherein this is a knee joint and this is a hip joint, we can make uses. So this is the stainless steel metal, which will be having the femur bone and the femur head, which would be implanted into the shaft of the femur. And this part is the acetabular socket, and that would be having a different configuration, and hence we use a different type of material for this, which need to give a cushioning sort of effect. So coming to cobalt chromium alloys, like major application is the dental casings. So in order to take the molds, in order to replace any teeth when it is damaged, or in order to correct any deformity in the tooth alignment and all those things, we have to take the molds first. So these cobalt chromium alloys, when we have two versions of it, one alloyed with molybdenum and one alloyed with the nickel and molybdenum put together. So when it is alloyed with the molybdenum, it is used for artificial joints, which is an orthopedic application, and also in dentistry in order to prepare the dental casing. And coming to the nickel molybdenum alloy, it would be used for load bearing effects, such as in the knee and hip joint replacements. In the stem processes, the one which we have shown in the previous slide, the stem processes of the femur is also made by the cobalt chromium alloy. There is a society called American Society for Testing Materials. So all the materials which are to be used as biomaterial will be regulated and standardized by this society. And these are the cobalt chromium alloys which are commercially available, and these are their trade names. Coming to the titanium alloys, the impurity contents in the alloy, that is pure titanium, will be alloyed with other impurities. So the other alloying materials would be giving it best features, such as high viscoelasticity and high wear and tear resistance and all such applications. So thereby we can influence the ductility and the strength with respect to the amount of alloying material being added to the pure titanium. And metals, they are hard metals, usually hard. So if we want, for few applications where we want it to have high wear and tear resistance and all those things, so we will have to make them a bit softer, a bit very soft in a way wherein it will not wear out on because of friction. So such element is titanium alloy, which is titanium 6, aluminum 4 and vanadium. So this is an alloy which is highly used for implanting materials, wherein aluminum and vanadium are alloyed to titanium in the weight ratio of aluminum 5.5 to 6.5 and vanadium 3.5 to 4.5. So here these are the various applications. Like this is the total femur, head and stem put together, and this is the stem part alone. Okay, and these are the various plates which are used for fixation, and this is also one area wherein we have the fracturing bones to be aligned together and then screw it up. So these are such applications shown here. These are different versions of them, and this is the scenario wherein how the bone is aligned and screwed up with the help of bone plates. So now coming to the properties: titanium, stainless steel, cobalt and titanium alloy with respect to the aluminum and vanadium are also showed here. And here important properties are their mechanical properties, and highly corrosion resistance is another important property, and their fatigue strength is another important property, and biocompatible anyway is the utmost required property for that. So metals having these features will be of highly usage in the medical applications. As I told you, the common demerits with the metallic metals being they cause allergic reactions, and corrosion is one other major drawback, and it being involved with very high fabrication technology, so the cost also increases. Coming to the polymers, we have three basic categories. One is naturally occurring polymer like silk, cotton, starch, cellulose, which we can extract from the plants. And on the other one, synthetic polymers, where we polymerize different elements and prepare a polymer which for our application. So those are synthetic polymers. Your Teflon, nylon, all these are examples for synthetic. And there is a category called a semi-synthetic polymer, where we make use of the naturally existing one, but we modify it in a way wherein like it becomes biocompatible, and thereby we can use it. In a crude form we can't use it. So that is the rubber is the example for such polymers. So in polymers we will be majorly interested in the physical properties, like how you are polymerizing it. So that will be defined by your crystallinity and the ability for it to resist the forces, tensile forces, compressive forces and all those things. And coming to the chemical process properties, the life of a polymer will be majorly depending upon the bonding strength, and this bonding strength would be the chemical bonding, and those would be the based upon the cross-linking strength. And apart from the other materials like other metals, other advantage of using polymer is they also possess optical properties. So for our lens applications and any of the ocular implants, we will be able to make use of this property. So these are the examples of polymers being used. So polyethylene, PMMA is best used as bone cement for orthopedic application. It being a polymer also, yes, we can use for cementing the stem processes of the hip joint. And high density polyethylene, wherein polymer is being used and polymerized in such a way that it becomes more dense, and it can be used for bearing the loads, and thereby it can be used in orthopedic applications. Teflon, that is the polytetrafluoroethylene, and polyacetyl are also other majorly used polymers. So coming to the merits and all, like since we have polymers have high viscoelasticity, so their creep resistance is of one importance, and their biocompatibility is other major important feature. Okay, and they are non-toxic and non-flammable and chemically inert. So these are the major advantages of the polymers. And coming to the disadvantages, yes, they degrade and thereby release debris, because they will be degrading and those particulate material will be creating a debris over there, and they are highly sensitive, so we have to take care of its degradation with respect to other factors. And their limited very low resistance and high wear and tear. So these are the major drawbacks, since basically degradation is the major drawback for the polymer. If we are able to control that, yes, they are the best suitable materials for medical applications. Coming to the ceramics are those materials which are engineered, meaning that man-made. So we fabricate them with a we fabricate them keeping in mind the application. So for what applications, what should be the characteristics of material. So based upon those characteristics, so what are the sources we have, so what properties can be used, or the what materials can be used in order to deliver these properties. So we engineer the materials in such a way that it becomes highly biocompatible for a given application. So few ceramics are refractory. They possess refractory and properties, and they are used as metallic oxides, carbides. Like we can have this possible in different forms. So the materials will be having wide variety of applications, and they are available in wide variety of forms, shapes, and all those things. So best examples for these are the alumina, that is the aluminum oxide, magnesium oxide, and silicon oxide. And it can also be fabricated in terms of ionic salts such as sodium chloride, cesium chloride, and zinc sulfide. And another major component where we use carbon compounds is to enhance the biocompatibility is the carbon based elements like diamond and other elements such as graphite and all those things. So these best feature of these carbon compounds is they give high mechanical strength. So we can make use of them, make use of their high mechanical strength, and can use for medical applications in orthopedics. So these are the few examples: alumina, zirconia, pyrolytic carbon, bioglass, hydroxyapatite, and all those things. The best feature of hydroxyapatite is orthopedic applications. The reason being, hydroxyapatite is a calcium phosphate element, and this element is available in the natural bone tissue. So the compatibility of hydroxyapatite towards the orthopedic applications is very high, and bone resorption and bone regrowth, all such applications are, or such these are the advantages when we use this hydroxyapatite as an orthopedic material. And coming to the other soft tissue applications, in the scaffold designing, we will be using them because of its excellent biocompatibility, good osteoconductivity, and also osteo generation. And since they are of high mechanical strength, yes, they can be used for orthopedic applications also. Disadvantages being, yes, depending upon the materials we use to fabricate, yes, we have a limit on the life of them, and their degradability, they are brittle and they are non-resorbable. And coming to the glass, bioglass and glass ceramics are one other category which are also used. So as discussed earlier, refractory properties are also delivered by these ceramics. So these are the elements which are used for refractory property. The fourth category is the composites. So wherein we have all features, all best features being extracted from the available materials, and they are fabricated in a specific fabrication technology in order to give a final product. So customization of design and customization of the material being used, these are the additional features of the composites. For example, if we take, like we have tooth replacements. So when we lose our teeth and we want to have an artificial tooth, we don't want that to be looking like any other artificial one. We want it to be appear as a natural tooth. The aesthetic look towards the implant is of major consideration. So, and for each patient, the color is different. The teeth are white, but yes, the shade is different for each and every subject. So, if we want to fabricate an artificial tooth with a color with as if it is a natural tooth for that patient, then yes, we need to include some materials and fabricate them as per that requirement. So, composites are designed in such a way. So whatever may be the composite, the basic fabrication of composite includes two parts. One is reinforced material and the other one is the matrix material. And the fabrication technology includes in fabricating a material by embedding this matrix material into the reinforced material. Reinforced material is the substrate material. Matrix material is the element, basic element which will be delivering the application. So if we see that, so this is the fiber, and this is the reinforced material, and this is the matrix material, and put together we have, like, the fiber is the original strength which will be giving the strength will be given to the material, and the matrix is like in order to enclose it, and the material which embeds into this reinforcement, and finally we have a fiber composite here. So if you want to take it in a normal generalized application, the laminates are best example. How laminates are prepared out of the wood pulp and all those things. In the similar way, we can think of these fiber materials also, which are fabricated as composites. Apart from these four categories, we have few other categories, special categories, which are also used as biomaterials. One of them is hydrogels. And we have the applications of hydrogels such as tissue engineering, drug delivery system, contact lenses, and all those things. So hydrogel is basically a gel base wherein we have the composite construction will be used. We have a reinforcement into which we have the matrix material. And apart from the hydrogels, we have biodegradable materials. So for few of the applications, like whether we want the material to be remained in the patient for shorter duration or longer duration, we have to define how it remains, or if you want to remove it, how it will be removed. So degradation is a process wherein we are making the material to decompose and come out of the human body. We want it to remain in the body for a specific function and for a specific duration. Example, healing of a bone fracture. Bone fracture healing takes a specific time, and if we are using a fixative plate or a fixative screw or nails, wires, whatever it be, a fixative device to hold the fractured bones together and make them heal, then the support of this material will be required for that particular duration. Say suppose that bone heals in a period of 1 month, then the requirement would be we want that material to support the fractured bones for a period of 1 month. By that time it will be healed and it will not be requiring any additional support further. So after that period of 1 month, we want that material to be decomposed and get out of that place. So we want them to degrade, and there are several techniques to degrade them, and it depends upon the material and its property how we can make them degrade. What is the difference between biodegradable and non-biodegradable? Is biodegradable are those elements which degrade in the biological environment. Body is a biological environment. So if we are able to make use of materials which can get degraded within the biological fluids and within the tissue environment, the environment which is composed inside the body, yes, then they are biodegradable. So that will be of major interest for us, because non-biodegradable, again, we have to cut open and remove those, which the patient will not appreciate. So that's the reason we'll go for biodegradable materials. It has to remain there, serve the purpose, and then after its function is accomplished, it has to get degraded. So these are the various materials and various polymer ceramics for biodegradable materials. Another version of degrading a material is we don't want to degrade it and get excreted out of the body. Another way of removing the material after its functionality is to get it absorbed into the body. So if a material is fabricated with the basic elements of polyglycolic acid and polylactic acid, yes, they can be absorbed or resorbed into the bodily fluid and get easily accommodated into the biological environment. So this is the chain of bioresorption. So we have to see that it has polyglycolic acid and polylactic acid. If it has these two, so by this chain, it will be completely absorbed into the body in terms of water and carbon dioxide. So these are the various other characteristics of bioabsorbable. It has high biocompatibility, permeability, they are non-toxic, degradation is controllable, and they can easily absorb into the body, gives high mechanical strength, tensile strength, and it also is inert without causing any adverse reactions to the tissue. So on the whole, to summarize, so I have given a table or the just applications. Ceramics, metals, polymers are highlighted here. And ceramics, we have discussed alumina, zirconia, calcium phosphate are of major interest. And metals, stainless steel, cobalt, and the applications are orthopedic and dental applications, hard tissue replacements. And polymers, we have wide variety of polymers which are used for soft tissue replacements. Different types of soft tissues can be fabricated by using these polymers. Bone cements, vascular grafts, contact lenses, coatings given to it, resorbable screws, which are the fixative devices, drug delivery systems wherein we want to deliver a drug into the tissue on a controlled rate with respect to time. Yes, your hydrogels are best example for that. And another area is to prepare the cosmetic products like any skin graftings, skin mandibular reconstructions, breast implants, and all those things. So these are the few references, the textbooks as well as the few sites are also mentioned, URLs are also given. So hopefully I have covered all the classes of biomaterials and have explained the different merits and demerits of this. Thank you for the class. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.